In this video, I'll show you how to use notation to help you think about Riemann sums using the context of a Mars rover. Here are the main points we address in the video. Left and right Riemann sums both approximate the total accumulation over an interval. Left and right Riemann sums can both be represented using what's called a sigma notation. Subscripts have to be added to the formula using sigma notation to distinguish between left and right Riemann sums. The Opportunity Mars rover is powered by solar cells to move around the surface of Mars. The rover is currently moving along a 100-kilometer path. As it travels, the rover kicks up dust which accumulates on its solar cells. The amount of dust that it kicks up depends on the composition of the surface it is traveling over. A rockier surface kicks up less dust than a sandy surface. The goal for scientists is to figure out how much dust will accumulate on the rover's solar panels. To do this, we use Riemann sums. In particular, we want to compute left and right-hand Riemann sums and write these using sigma notation. To do this, we first divide rover strip into equally sized intervals. In this case, each interval is 20 kilometers long. We'll look at our data that shows the rover's position along the path and the rate of dust accumulation. And we'll add the column to note the length of each interval. We'll write P for rover's position along the path and R of P for the rate of accumulation at position P. So for example, R of 0 is 6 milligrams per kilometer, R of 20 is 3.5, and so on. Then the amount of dust that accumulates over each interval is approximately the rate for that interval times delta P. We can compute these products for each interval. So for example, we travel 20 kilometers at 6 milligrams per kilometer for the first interval, which gives us 120 milligrams of dust. We can do this computation for each of the intervals and then add these up to compute the total amount of dust has accumulated. When we're doing these computations, we're using the rate at the beginning of each interval. So we're creating a left-hand Riemann sum. Let's use function and sigma notation to write this sum. For the first interval, we multiply the rate at the beginning of the interval by the length of the interval. For the second interval, we multiply the rate at 20 kilometers by change in position. And we continue to do this for all the intervals. We write the symbol sigma to show we're adding these up. And the things we're adding up are R of P times P. And we figure out that this is all equal to 310 milligrams. It's important to note that here we did not use the rate at the 100-kilometer mark. We only took the rates at the beginning of each of the 5 intervals. We could also use a rate at the end of each interval to do our calculation. For example, for the first interval, we multiply 20 kilometers by 3.5 milligrams per kilometer to get a total of 70 milligrams of dust. We could do this calculation for each of interval, then add this up to get 210 milligrams. This would give us a right-hand Riemann sum, which we would write using similar notation as our left-hand sum, except the rates would come from the end of each interval. Now, this seems a little odd. If you look at these two terms, they use exactly the same notation. However, in the first case, you get 310 milligrams and you get 210 milligrams in the second case. If you just saw this notation, how would you know which number was correct? Clearly, our current notation for Riemann sum is not sufficient to distinguish between right and left hand sums. So we need more notation that help us figure out what's going on. We know that total accumulation can be approximated by a left Riemann sum. Now I'm going to introduce some labeling on our observation of rover strip. I'm going to label the 0 kilometer mark as p sub 0 just to distinguish from other values of p. Then I'll write p sub 1 to indicate 20 kilometers mark, and so on. Now, when we're computing the left Riemann sum, for the first interval, we would evaluate the rate at p sub 0 and multiply by delta p. Then for the second interval, we would evaluate the rate at p sub 1 and multiply by delta p. Then repeat for the third interval using p sub 2, and again for the fourth interval using the left endpoint, p sub 3. And then for the last interval using p sub 4. Now, how do we write this all using the sigma notation? We'll use letter k to indicate the value of subscript. So for the first interval in this sum, k would equal 0. For second term, k will equal to 1, and we'll continue for the rest of the terms. So if we write this sum using sigma notation, in each term we're multiplying r of p sub k by delta p. And the value of k starts at 0 and ends at 4. We indicate this by writing 0 below and k above of the summation symbol. And we'll later compute that this is equal to 310 milligrams. We can also approximate the total accumulation using the right-hand sum. We'll use the same process as a left Riemann sum, but use the right endpoints instead. So for the first interval, we find a rate at 20 kilometer mark, which we label as p sub 1. For the second interval, we compute a rate at p sub 2, then at p sub 3 for the third interval, p sub 4 for fourth interval, and at p sub 5 for the last interval. If we use k to indicate the value of subscript, then the first term corresponds to k equals 1. The second term corresponds to k equals 2, and so on. Using sigma notation, we're evaluating rate at p sub k and multiplying by delta p, but this time we're using starting at k equals 1 and going up k2 equals 5, which indicate by writing these below and above the summation symbol. And we previously calculated that this equals to 210 milligrams. In summary, we have labeled the endpoints of each interval using a subscript. In the left-hand sum, the subscript starts at 0 and go up to next to the last one. In the right-hand sum, the subscript starts at 1, and go up to the last one. So now we have a way to write Riemann sums that distinguish between left-hand and right-hand sums.